Sorry about the delay getting set up. I'm convinced this. I run Linux on my laptop, and for years it always used to be my fault. These days, the stuff is so reliable, and it's HDMI as well, so it should just work. So I'm refusing to blame my laptop this time. But anyway, thanks for your patience. Okay, so I'm Sabin. I'm one of the co-founders of Type Level. I'm also part of a Scala consultancy called Underscore. As people may have learnt either via Twitter or over the or various people mentioning it yesterday, I'm going to be doing some work with EPFL, Martin's group, on DOTI, or Scala-3, as we should all start calling it. I have, for the last year, been doing a certain amount of work with Lightbend on Scala-2. And a lot of the work that I've been doing in that context is trying to sort of pull the sort of distance between Scala-2 and Scala-3 together. So there are various things which are arriving in Scala-2 in 2.13, which are either already are or planned to be features in DOTI. So kind of. I guess the context for a lot of the work that I'm doing is thinking in terms of what we are going to need to be able to do to bridge the gap. And some things I think are going to be very straightforward. I mean, John just gave us a very nice example of doing a cross build between Scala and DOTI. For stuff which is fairly straightforward, Scala source, which is just using the language. I think the transition story is actually going to be really quite smooth and quite straightforward. Where things get more problematic are where people are doing things extra linguistically. So that means working with things like macros, working with things like Scala compiler plugins. The current Scala-2 macro system is inextricably tied up with the internals of the Scala-2 compiler, and this I think has been for some number of years now really deeply problematic, because really it means that it means there can only be one compiler in a sense, because if you're going to provide a full implementation of the Scala macro API, you need to provide essentially the same internal representation, and this really ties your hands quite seriously in terms of your freedom to evolve the language, to change the way that to change the implementation or change internal representations of one sort or another. Now, okay, so what's the problem? Sure. So why is this a problem? Well, it's a problem because over the last significant number of years, large parts of the Scala ecosystem have made really quite essential use of macros. That includes myself. I mean, Shapeless uses macros in ways which I think it is absolutely inconceivable that the way that Shapeless uses macros could be directly translated to a mechanism in DOTI. It just simply isn't going to happen. And that is true of a significant number of other parts of the ecosystem which are using macros in similar kinds of ways. So what to do? So the conclusion I came to a few years ago was that for this reason and others relating to limitations, primarily performance limitations on the way that the current Scala-2 compiler handles the kinds of things that I do in Shapeless. So, for example, using recursive implicit resolution induction based on implicit resolution to do type level programming. That really the only feasible fixes were basically to try and move primitives out of macros in Shapeless as a library into primitives actually as part of the in the compiler itself. So that's kind of work that is this going to come back? Oh no. As part of the compiler itself. So that's work that I've been doing in Scala 2. So there's a couple of things which have recently landed in Scala 2, which directly relate to that. So the work I've done on biname implicits, that is pretty much a complete replacement for Shapeless's lazy. Shapeless's lazy is a sort of a primitive macro which essentially allows you to tie inductive knots, which allows you to say derive type classes for recursive types. I don't know what we're doing here. And another aspect of it has been the work on literal types that I've done, which replaces a lot of Shapeless's use of singleton types. And there's a collection of macros in Shapeless which relate to singleton types. So those things are now language intrinsics, and there are also things which are, because these features are present now both in Scala 2.13 and also in Dotty, they're things which are now portable between Scala 2 and Scala 3, and this is great. That combined with some performance improvements in implicit resolution, again, which are present in 2.13, and which either are or could soon, very soon be features of Dotty as well, means that we can slowly imagine, we can see the sort of the proportion of Scala of Shapeless which consists of macros shrinking dramatically, and the proportion of it which is directly portable to Scala 3 growing. And this is kind of a process that I want to try and continue and try and get to a point where we really don't have concerns about macro portability in Shapeless anymore. And to the extent that other parts of the ecosystem depend on Shapeless, smoothing the transition for Shapeless transitively smooths the transition to Scala 3 for those libraries as well. And hopefully the kinds of things that we come up with will be generally useful to other projects as well. So I would, at this point, be wanting to show some slides. I don't know what to do about this. Unplug and replug it again. Turn it off and on again. Yeah, I'm sure it is. Yeah.
So you can even change slides, nobody will see them, but they'll be recorded. Okay, now it's trying to get it back.
Okay.
All wrong, but there are ways to reset. Is this kind-polymorphism?
Maybe we can have half on that screen and half on that screen. Oh, come on. Okay, so while this is continuing, I will more background. So basically, most of the macros in Shapeless are gone now, effectively, or at least in principle, they can be removed. So lazy, we can replace that with biname implicits. All of the singleton type stuff we can replace by literal types. All of the sort of the compile time performance improving macros, they're replaced by some of the work that I've done on implicit induction in the Scala compiler. The one remaining primitive is generic. So generic is the component of Shapeless which will take you from a chaos class or an ADT into a generic representation which you can then compute over in a general kind of way without being concerned about the specific identities of the types that are involved in it. So this is the one final little primitive. And kind of almost seems tantalizingly close that, well, could we just bake generic into the Scala compiler, Scala 2, Scala 3, and we're done. And then essentially all of the parts of Shapeless which are currently implemented in terms of Scala macros are now implemented in terms of language intrinsics, and everybody's happy. And I can leave the horrible gnarly internals of various bits of Shapeless macros as they are, and rely on the evolution of the compiler. Okay, so the last remaining bit of the picture for eliminating all of the macros from Shapeless is generic. So the real problem we've got with this, as I will sort of come to, is that the earliest form of generic kind of looks very, very simple and straightforward. You give it a type, it will give you back a representation. However, there are many, many other kinds, not being pun intended, of types that one might want to derive a generic representation for. And as we're going to see in a second, this is going to cause problems. So anyway, I'm just going to, that's some background which I would have come along with, but anyway. Now we're going to talk about what is kind-polymorphism. It's a form of parametric polymorphism, and we can say that type parameters of this sort, so let's say the type parameter that you find in a simple type constructor, say the list type, it's of kind star. And the type parameters here are type parameters which do not themselves have any holes. So they're simple complete types. So you can substitute anything in for t, which is a simple complete type in its own right. So for example, int or string or Boolean, or for example, some other but fully applied type. So you could have a list of and then list of int. The key thing here is that the type that the list type constructor is applied to is itself a complete type. Scala has higher kinded types. So we have type constructors which have different kinds. So in this case, we have, for example, something like a functor will take a type parameter which itself takes a single simple type parameter. So for example, we can have a functor of a list. So list has a single simple hole. Option has a single simple hole. Vector has a single simple hole. And we say that types of this sort are of kind star, arrow star. Can we abstract over that? Is there some way of providing a hole in a type constructor which could be filled by type arguments of different kinds? So for example, there is in the Scala reflection API, there is a representation of types called type tag. So if we want to reify in a macro or in a Scala compiler plugin, if we want to reify a type, we implicitly ask for a type tag corresponding to that type. But of course, types themselves, they can be different kinds. So what we kind of want to be able to do is say, give me a type tag for an int, but also give me a type tag for list the type constructor, as opposed to list of some particular type, like list of int or list of string or list of any or list of a wildcard of some sort or another, some existential type. And again, maps on through the complete bestiary of possible different kinds of types that you might be able to represent in Scala. So that's the kind of thing we want to be able to do, at least for things like this. And the problem is that actually we can't do that. There is no direct way of expressing that kind of polymorphism in Scala. We are not able to abstract over different kinds. We can do this in Haskell. Haskell has one of its numerous extensions, this something called polykines. Haskell has an example here is Haskell's typable type class. Typable is kind of it's essentially a type-safe casting kind of operator. It will take a value of some unknown type onto an option of a specific type. Typable is something which it's a little bit like type tag in a way, in the sense that it can be indexed by types of different kinds. And in Haskell, we're able to represent this directly. So you can have a typable for int, but you can also have a typable for this, which is Haskell's representation of the list type, and so on and so forth for types of other kinds. So, okay, that's what it is. Why? I mean, what's the reason? I've sort of hinted that there are some sort of conveniences and some rather obscure kind of edge cases. Well, looking back at that Haskell example, the reason you want it is because it allows you to reduce a certain amount of boilerplate. So, if we didn't have the ability to index typable by types of different kinds, we would end up having to duplicate the type class itself for every single kind you wanted to be able to apply it to. So, for example, we can have typable for types of kind star, typable 1, say, for types of kind star, arrow, star, typable 2, typable 3, typable 4, and so on. To do this in full generality, we would need to manually duplicate those definitions for all possible kinds, or at least all kinds of interests. Well, what kinds are of interest? And that is a tricky problem. I think in a particular application, and maybe in a particular library, you can have some idea of a sort of a fixed universe of kinds that maybe you care about. But if you're talking about a language primitive, it's not kind of obvious where you're going to stop. So here's another example. This is an example from Scala rather than Haskell. So we have a type of operator. Again, this is used in Scala reflection. It's used in macros. It's used in the plugin API. Where again, similarly to the type tag example, we want to be able to reify a type argument. Suppose what we actually want is type of the list type constructor, so the last line, that's what we really want to do. We're not allowed to write that because type of is indexed by a type of kind star. So we have to sort of fake it somehow. And you'll typically fill the hole somehow. You can stick an any in it, or you can stick, that will give you a fully applied type, and then you can sort of poke the any out and get the wrapper by using the type constructor method to extract the type constructor from it. You could also try and I mean, this is something that I've actually seen as a bug in macros. You can use an underscore, which in this context means a wildcard, which means that you actually get an existential type, which is kind of the wrong thing to have. It looks like it's sort of saying what you want it to say, but it's actually not giving you the right type. Okay.
Could do something between the type tag for the existential and
no.
the type tag.
Yeah, exactly that. And Shapeless has a typable which is very similar to Haskell's and has the same issue. Okay, is that really compelling? I mean, is that a big deal? What's about these little bits of boilerplate that we've got? And I kind of think, for the example we've seen so far, it's actually not that compelling, and the boilerplate isn't so bad. But maybe that's just because we're looking at some very, very simple examples, and that things get more interesting a bit further out. So in Shapeless, I've kind of run ahead of some of this already. In Shapeless, we have a type class generic, which is basically the mechanism which allows us to map between ADTs and a general representation of them, which sort of strips off the specificities of their type and just allows you to work with a general representation in a very general yet type safe kind of way. So a generic for some type of kind star, G, is a type class which provides you with a representation type, which again is of kind star, and a pair of methods which will project you into the representation space, so which will take you from take you to a value of the representation type from the ADT, and vice versa, which will take you from a value of the representation type back to the ADT. So the kinds of thing that you can do with this, so for example, you might be able to sort of write some kind of general concatenation kind of method, which will basically stick a couple of case class values together and tip them into a new case class. This kind of thing, people do this kind of thing for doing sort of schema migrations. There's some very nice libraries that are built on Shapeless which do this kind of thing. So say you have an old schema for an old row which has got an int and a string in it. You want to add a new column which is a Boolean. So you're going to end up with values of your two old case classes, and you want to basically glom them together to give you an instance of C, which is the case class which includes all the elements. So you can write a general function which will take an A and a B and give you a C for any types A, B, and C. Which have instances of the generic type class available. And you can do that in a fully type-safe way, statically type-checked, no runtime reflection, and this is a useful mechanism. GHC, that's the Glasgow Haskell compiler, the main Haskell compiler that almost everybody uses, has a generic feature which is quite similar to this, and it was to some extent an inspiration for generic in the form that it appears in Shapeless. Okay, well, at the outset, Shapeless only had representations for types of kind star, as that trait demonstrates. And you can see that that's the case just by looking at the type parameters, the form they are there. They are simple type parameters. They're not type constructors of any sort. And that is going to show up both in the type of the ADT, the case class, the sealed family of case classes that you feed into it, and also in the representation type. Both of these things are fully applied. It covers a lot of ground. Most of the uses of Shapeless for doing the standard sort of codec type stuff, serialization and deserialization stuff, which is popular in libraries like Circe and so on and so forth, make good use of representation types of kind star. However, there are a bunch of other extremely interesting things that you can do when you start looking at types of different kinds. So one of the things that I wanted to enable was as well as derivation of type classes of the codec kind, but all more interesting type classes of the kind that you find in libraries like cats. So, for example, deriving functors and so on and so forth. And for this, we need a generic which actually allows you to index by a type with a hole in it, because a functor is indexed by list or option or whatever. That's a type with a type constructor itself, sorry, a type parameter itself. So if we're going to produce a generic for that type constructor, we need a generic which is able to capture a representation which is able to produce a representation which itself has a hole in it. And for this, we end up with this type. This has been in Shapeless for a few years now, generic 1. You may recognize the 1 from the other earlier example that I gave as being a sort of a hint of the problems to come. So again, you can see in exactly the same way as the original generic that you can read off of it that this is a generic suitable for types of kind star, arrow star. And here you get the type we're going to be representing. It has a hole. The representation type has a hole, and we also end up with the to and from methods being polymorphic themselves. So, for example, we can only our values that we work with, they have to be monomorphic, they have to be complete values. But that means that the methods dealing with them will have to provide a type parameter to, 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 to complete the type constructor that we're working with. So this allows us to derive instances of type classes like functor or foldable or traverse, and the library kittens, part of the cats ecosystem, is a place where a lot of that stuff has been worked out over the last year or so. I'm not going to do a demo. I'm not going to have time for that. Okay, so everything's fine, right? So we got. Okay, it's kind of unsatisfactory having a generic and generic one. Can we actually stop there? Must we stop there? I think we can have some very interesting types where we might also want to be able to do exactly the same kinds of things. So here is an example of something called a higher order functor. In the Haskell world, it's known as an H functor. I believe that the form it exists in a pull request for cats. It's called functor K. It's not merged yet, is it?
No, it's in cat's tag list right now.
Oh right, okay. But it's kind of an interesting thing. So a functor K is very much like a functor, only instead of mapping an ordinary vanilla function over a container or a structure of some sort or other, you're going to map a natural transformation over a structure. And this is the kind of thing that allows you, instead of sort of poking out sort of complete types out of a data type, it allows you to kind of change some sort of wrappers and envelopes. So here's a problem that I think probably most of the people in this room will have had at some point, which is how do you represent in your user interfaces a piece of partial data? So we're filling out an address or something like that, and during the course of doing it, you will have a situation where you've filled in a name, filled in the sort of first line of the address, but there's some other bits of it which are not yet present. So how do you represent that? I don't know. There are lots of ways of doing it. You could wrap everything in options. Some people have said, when I've done polls on what approaches people take, is that they use sort of shapeless records and sort of construct something like that. But basically, the normal choice is to wrap things in options, or maybe horror, use nulls or something like that. That would be a terrible idea. But one quite popular approach, I think it's probably more popular in the Haskell world than it is in the Scala world at the moment, but I think it's catching on a bit, is this idea of constructing a little F algebra. And that sounds fancy, but basically all it means is that you just take your data structure and you thread a type constructor parameter through it. So here we've got an order. And conceptually, the order there's an item, sort of something, the thing we're ordering, and a quantity. So the item's going to be a string, the quantity is going to be an integer, and a normal vanilla definition of such a thing would have no type parameters at all. But we add this f type constructor type parameter, and we just wrap all the elements in it. Now, the nice thing that we've got about this is that we can have depending on what we instantiate f as, we can either have an order which has optional components, so we can instantiate f at option, or we could instantiate it at id, so the identity type constructor, which basically takes id of t is just the same as t, which represents a complete order. So the idea might be that you go through a process whereby you start with an order indexed by option, and you fill out the components, and then at some point you apply a natural transformation which takes you from, actually option isn't going to work here, but something related to option will, which will take you from an order indexed by option to an order indexed by ID. So once you've got a complete thing, then you can just reuse the same data structure rather than duplicating it. In one case with options, in another case with fully complete values, and you can essentially map with a higher order functor over these things. I will show a little bit of code here because that will probably be helpful if I can actually do that. So. Suppose, for the sake of argument, we have an option with a default. So basically, we've got either a value of type t, or it's defaulted to some default value. So the idea there might be that we start with a partial order. So we've got some fish, and we're defaulting to just one unit. So this is going to be an order which is indexed by option of D. Ultimately, once we finish doing our UI stuff, we're going to end up with an order of ID. And we can do that just by mapping a fold operation over the contents of this data structure. So that's fine. The nice thing is that for many data types, in much the same way that we can derive automatically, say, a functor type class instance for, say, a list or an option or whatever, we can also automatically derive these higher order functors for data types. So you could kind of get this kind of stuff for free, which is actually very nice, I think. So it's a very nice property. However, what is the kind of this thing? It's not star arrow star. It's star arrow star arrow star. So it's and once you observe this, you realize that, oh my God, there is this whole entire universe of kinds out there. Another thing to bear in mind is that one of the ways that Scala represents bounds on type parameters is effectively as kinds. So, for example, I'm sure people have had the experience of working with an API which has sort of bounds on type parameters and discovered that those bounds have tended to sort of propagate throughout their code because basically to conform to a bound on a type parameter and a type variable, basically the type argument has to have bounds on its components which correspond to those, and these generate huge numbers of families of kinds of types, in a way which is actually rather worse than it is for Haskell. I mean, Haskell has the same problem well, it has this problem here, but we actually also have the issue with sometimes generating bounds as well, which is something that Haskellers don't have. Okay, so here's the problem. If you want to add generic or something similar to it as a language primitive, it seems to me to be extremely unsatisfactory to pick this sort of rather arbitrarily small subset, generic 1. I think is not enough. I think it's arbitrary and limiting. I think we need to have some way of capturing generic in full generality. And I think it's possible to be ad hoc in a library. So shapeless can be ad hoc, but I think a language feature needs to be orthogonal. It needs to be consistent. It needs to be general. And I think doing this in an ad hoc kind of way is essential for it being a language feature. Okay, so that's bringing us back to where I started, which was if we're going to eliminate all the macros from shapeless and related libraries, we need to have an appropriate set of primitives in the core language. And if we're going to have an appropriate set of primitives, we need to have the right set of abstractions to be able to make that work out smoothly. And my argument is that it is an essential part of the abstraction for generics that we have Kind-polymorphism to help us with the problem. How much time do I have now, roughly? 20 minutes, okay. Okay, so can we abstract away any of the differences between the kinds that we've seen? So here are the sort of the, so we kind of want to write a single generic type class which is able to capture at least these two patterns, but obviously, ideally, all of them. At the moment, there is literally nowhere in a Scala program that you can write there is no context which can be filled with both a type of kind star and a type of kind star arrow star. Once in the ancient history of Scala macros, there were things called type macros, which they did actually give you a place where you could put a type of more than one kind. Actually, there is an exception to this, which is nothing and any. Nothing and any are both polykinded, but they're kind of exceptions. Okay, so what we could try and do is try and erase the differences. And so this is before we look at kind-polymorphism. I mean, can we actually approximate it somehow or other? We can sort of do something. We can come up with a family of wrappers. So we can say wrap types of kind star in a sort of a kind star wrapper. We can wrap types of kind star arrow star in a kind star arrow star wrapper. And because these things then end up, all the wrapped types, they all end up being types of kind star. Okay, we've brought some uniformity into the picture. So we could start imagine then that we have a generic which is indexed by these types which have their kinds, as it were, encoded in their type in a slightly different in a different way. So we can do that, and then we can sort of imagine some way of capturing the idea of applying one of these encoded types to a type parameter, well, one or more type parameters, and we can sort of do that in Scala using GADT. So we can imagine capturing an apply of a type of kind star. That's basically going to ignore its argument. We can imagine applying a type of kind star arrow star, which is going to give us back an instantiation of the list type parameter. This is all kind of quite clunky and ugly. It kind of works. You could end up then with a version of generic, which sort of looked a bit like this. So you would again, so this looks like generic 1. Everything is in terms of types of kind star arrow star. We've added a single type parameter here to our to and from methods. This kind of doesn't really work, but it sort of does a bit. And we're going to then encode type application in the to and from and the result and argument types of the methods here. And so we can get something that looks like this. This is very clunky. I'm not going to show you the demo. It kind of works. It's pretty clunky. Okay. So a while ago, Pascal Voiteau, who is otherwise known as Mandubian on Twitter and GitHub, we, sort of frustrated by this, decided to see if we could take a very, very quick swing at producing a proof of concept implementation of kind-polymorphism for Scala. And the idea was to do the absolute minimum to make an interesting difference. And the absolute minimum was basically to solve that first problem, that there is literally nowhere in a Scala program that you can put types of different kinds. And so that's what we did. So we can provide, there is a mechanism for expressing type parameters which can take type arguments of any kind. The idea then would be to use, rather than to have additional language features, to use sort of type level computation of the sort that you do with implicits, similar to how you work with types in shapeless. So no additional sort of type level primitives in the language. And we wouldn't go as far as polykinded application. So we left that bit and see if we could get enough excitement out of that to make this a compelling language feature. We put together a proof of concept. Most of the work was done by Pascal. It ended up in type level Scala. And was iterated on a little bit. Pascal did a whole bunch of very, very exciting experiments with kind-polymorphism for various purposes. So generic ends up looking like this now, and you'll notice that we have here a bound here of any kind on each of the type parameters, which means that now generic can be instantiated for types of kind star arrow star, the H functor, the kind of the H functor that I showed earlier. All of these things are now possible. And instantiations of this type can then look like this. But notice also that because we decided not to address type application, you still end up with that clunky encoding of type applications. So again, I'm not going to show it. It makes things a little bit better. It's still quite clunky. and we decided that it wasn't really offering quite enough sort of power to weight ratio to really be worth pursuing. However, it was adopted in DOTI, or rather, should we say, scala-3, for various reasons. So one of them was that actually it turns out that there are some quite nice sort of internal theoretical purposes within the way that DOTI represents types, which are actually fit very well, very nicely with kind-polymorphism. John actually showed an example of that with you had the polychided bounds there. Yes. So with that itself it's related. The fact that is something which is possible in DOTI is.
To ask actually, I don't know if this is the right moment, but
whatever. I'm totally off script now. Anyway, so.
Requires unification, which is very simple, relatively simple for proper kind of types. But for high kind of types, you have more choice, and I imagine the deeper your kinds are, the more arbitrary the choices in how you unify those types would be.
Well, I think the approach taken in the partial unification is actually it's not perfect, but it's good enough for that. There's a whole huge research literature on higher order unification, which addresses that. But the simple rule of solve greedily from left to right is actually works pretty well and is fairly predictable and understandable, and that generalizes to this stuff reasonably well. Yeah. Yes, it does. Anyway, so the version in DOTI it doesn't actually take us any further than the example I just demonstrated I just didn't demonstrate with the type level Scala compiler. But basically, this is effectively with a -y switch on the DOTI command line is actually legal DOTI. Basically, the implementation was very, very similar to the type-level prototype and was somewhat inspired by it, although the internals are completely different. But this has absolutely revived our interest in sort of pursuing this further. We've been given an inch in terms of the polychided bounds. Well, maybe we should actually see if we can solve the second problem. And the second problem was polychided type application. That was the second issue that we had that was resulting in the boilerplate. So what we've got here, so this is a polychided generic. We've got bounds of any kind here. We've got bounds on the represented type and the representation type. So the noise is in all this stuff here representing application of the type constructor to some number of type arguments. Okay, and then so a representation of this. I haven't actually shown you the box. The box is basically an option. So nothing particularly fancy here. So we can kind of represent this in an encoded way, but this is the noisy part now. Can we eliminate that? And I think the answer is we probably can. I think we can arrange things so that we have type parameters of this form. So this is a type parameter which has an any-kinded type argument applied to it. If we can express a constraint that the type of the representation the kind of the representation should be the same as the kind of the type being represented, and we can infer from the application of G and repr to I that I must represent some number of type variables of in turn appropriate kinds, which when the type constructors are applied to them, produce well-formed types of kind star. At which point, I think basically we're home and dry, and we can actually represent then particular instances of generic. So here one for this thing, which is basically an option. I think we can capture that directly. We simply have to arrange things so that a particular instantiation of this is treated as a suitable subtype of the polykinded generic trait. And the nice thing here is that actually erasure is our friend, because all of this stuff goes away during the compilation process. So the kinds all disappear, the type arguments disappear when stuff is mapped down to the JVM. So in terms of actual implementation, you look worried.
I was just thinking that because of erasure, you only have the possibility of ever writing proper types to bytecode. So you have to combine like one kind with a whole of the same kind and put them together so they annihilate.
Yeah, absolutely. Yes.
In order to be able to ever produce something that could.
Absolutely, yes. But as far as the runtime is concerned, that's all done and dusted. So this is purely something that we can deal with during typing, which is fine because we've got lots of room to maneuver there. And in terms of the implementation, you probably end up with sort of generating bridge methods and things like that of that sort that you see already in various bits of Scala's encoding. I'm not going to explain what those are because they related to a demo that I haven't had time to show. Okay, so what's the status of this? Well, there's an implementation in type level Scala. There is an initial implementation in DOSI. Neither of those currently cover polykinded application. So some experimentation with polykinded application would be well worthwhile. It needs to be written up as a SIP. I mean, even in DOTI, it exists only as something which is behind a -y flag. And then we need to see how we can use it. And obviously, the thing I want to use it for is to produce a polykinded generic, which will hopefully get to the point where we can get rid of all of the macros from Shapeless. And that's where I want to get to. So that's it. Questions?
Who would have guessed? Thanks, Phil. Could you abstract over context bounds? It's the first question.
That's a really interesting question. What you're asking for is the kind of a type which has a particular implicit available for it.
Well, just going back to the comment I made 5 minutes ago.
No. I mean, yes. The answer is GHC does that. There is something called constraint kinds in GHC, which effectively capture the idea of the kind of a type which has a particular type class instance. So, in other words, encoding the presence of a type class instance in a type. This is one of the ways that GHC sort of comes back round and tries to sort of rediscover things that you can do in Scala because Scala doesn't have a first-class representation of type classes. You could absolutely do the same thing in principle in Scala. You could represent a kind of types with a particular type class instance, and you would probably end up with something which looked a little bit like implicit function types. And I've kind of discussed the relationships between implicit function types and constraint kinds with various people at EPFL, and there are sort of vague inklings that there might be some kind of relationship between the two, but it's a little bit up in the air.
Okay, and my next question is a little bit frivolous in that. I think I know what the answer is. Would there ever be a need to consider in the type system existential kinds, and hence kind scolums? And hence kind scolums.
Kind scolums. I think probably yes. Yeah, I think I wouldn't actually be surprised if they aren't already there in some form or another. I'm sure, Paolo, you must have a question.
And what's existential kinds? I mean,
for the record.
Why do you say that you would expect existential kinds there?
Well, in Mars's example, you have the I parameter, which was the I parameter was the method,
which could be existentialized if you could
Well, it's going to be. So we've got quantification of the kind. So we've got universals. So you've got universal. You're going to get an existential somewhere. Usually.
You can quantify over types, though. The ones can be quantified over types, and their bounds, their upper bounds, but all the kinds are called as upper bounds.
Well, so that is the interesting detail in the encoding and dotting for sure. But there's probably something corresponding.
Variables of which represent which extensions, but their own type.
Yeah, sure. Yeah.
Which makes hopefully things simpler.
Yeah, sure.
Like more features you ask, the more we start worrying, is this going to be sound?
Well, I think the kind polymorphism. I mean, we never actually discussed this, but I'm thinking that the schema that Martin's come up with, mapping things to upper bounds, that has to be safe. We're not going to get Girard's paradox because we're not creating any new types. We're just mapping stuff into a subset of the existing universe. That must be safe.
I've been more and more convinced of that. Right. I think this is becoming a pretty narrow conversation, but yes.
Just a little bit.
Yeah.
Okay. Any other questions? Do we have time for any more?
Just one more. Everybody's puzzled.
Well, you can come and ask.
I'm the first one to be puzzled.
You can come and ask me questions during lunch or at any time during the day.
Okay, thank you so much, Miles. And thank you for your patience.